Let's continue into our thermochemistry. We're going to take a look at phase change with the heat diagrams. This idea is pretty much latent heat and specific heat put together. So we're going to have temperature changes and state of matter changes happening in one event. And we're going to use heat diagrams to help us organize that information. So a phase change is going to be when you heat or cool a substance and the temperature changes enough that it causes a change in the state of matter. So you heat or cool a substance until a state of matter change occurs. So what we're going to see is a substance going from a liquid to a solid, solid to a liquid to a gas, gas to a liquid, as we heat or cool down a substance. And we're going to use a heat diagram to help us keep up with this. So a heat diagram is just a graphical representation of the energy exchange, whether it's coming into the substance or leaving the substance. So it's a graph of the energy exchange or transference. So when you have a heat diagram, it's just a basic XY plane graph, not too fancy. On your graph, you'll include a boiling point or condensation point and a melting or freezing point. So this will be my boiling point of the substance. This will be my melting point. These 2 points are important because once your substance hits this area, it's going to go through a phase change. So for instance, if we were heating a substance from, say, room temperature, and the temperature was increasing as it gains energy, once it hits that boiling point, the temperature will stop. Because now the energy is not going to causing the molecules to spread out and move more. It's going towards breaking intermolecular forces. So this line will go flat because the temperature is no longer increasing. Even though you're adding energy, the temperature is no longer increasing. Once those forces are broken, the temperature will start going back up. So at this stage, we'd have a liquid. At this stage, we would have a gas. And then this flat area is the transition between, and that's called your phase change. So in order to figure out the energy that was transferred in these areas, we use our specific and latent heat formulas. For any incline, we use MCAT, or Q equals MC delta T. So incline and declines on our graph, we use Q equals MC delta T because it's a temperature change. And for the flat areas or the planes, that's going to be your phase change. That's going to be your latent heat formula because there's not a temperature change anymore. So if you have a flat plane, it's Q equals ml. And then once you find all segments of your graph, you simply add those energies to find the sum. Just add them up to find the total. And that total energy is how much energy in the system that was transferred. So let's look at a simple problem first. It says H2O is at -5 degrees Celsius and is heated past boiling point until it reaches 110 degrees Celsius. Draw the heat diagram of this event. So let's just draw an easy graph. So there's my XY plane. So my lowest temperature is -5. So at the bottom of my graph, I'm going to put -5 degrees Celsius. My highest temperature is 110. So at the top of my graph, I'm going to put 110 degrees Celsius. We need to include our melting and boiling point. The melting point of water is 0 degrees Celsius, or you could say the freezing point. The boiling point of water is going to be 100 degrees Celsius, or you could also say its condensation point. Now, I did not draw these to actual scale because that's not what's important really. What's important is more of how much energy is going into and out of this system. So the scale of the graph isn't as big of a deal. So let's start by drawing a graph. So at -5 degrees, our ice is heating up. It's heating up. Once it hits 0 degrees, it starts to melt. The temperature goes flat for a moment. Once all the ice is turned to water or liquid, it starts heating up again. It's heating up, it's heating up, it's heating up. Once it gets to that boiling point, the energy is now going to break in forces. It's no longer heating the substance. So this graph again goes flat. Once all the ice is melted, temperature starts going up, until we reach that 110 point. So that would be the heat diagram of this event. Now, if we were looking to solve for the energy of this event, it'd be pretty simple. So I'm going to label these segments 1, 2, 3, 4, and 5. So in order to figure out the energy, you got to figure out the energy of these individual segments and then find the sum. So at position 1, that is specific heat because it's an incline or a decline. In this case, it's an incline, so we'd use Q equals MC delta T. At point 2, it's a flat plane, so we'd use Q equals ML. Point 3, it's another incline, so Q equals MC delta T. Point 4 is another flat plane. We'd use Q equals ML. And 5 is another incline. We'd use Q equals MC delta T. Once we find the individual energies for these segments, you'd add them all together to find the total energy. So the Q total, or the QT, is Q1 Q2 plus Q3 plus Q4 and finally plus Q5. Doing this is going to be very tedious and repetitive, but it's fairly simple once you get going. So inclines and declines use specific heat with the temperature change of that segment. For flat planes, use the latent heat of that substance, and make sure you pay attention to which plane or flat plane, which segment is the vaporization point, which one's the fusion. So the one on the bottom here, that's going to be the fusion point, so I need to use heat of fusion. One on top is the vapor point, so I need to use heat of vaporization. And then for the segments, the inclines, I would use that specific temperature. So this segment in particular goes from 100 to 110, so the temperature change there is 10 degrees Celsius. This middle segment, temperature change is 100 degrees Celsius. And this last segment, the temperature change would be 5 degrees Celsius. So make sure you use the individual segment temperature changes. All right, let's look at another problem. So it says an ice cube at -20 degrees Celsius is heated to 20 degrees Celsius. How much energy was absorbed in the process? The heat capacity of ice is 2.11 joules per gram degree Celsius. So first thing I'm going to do is draw a little heat diagram to help me keep my information organized. So I'm at -20 degrees Celsius. I'm going to 20 degrees Celsius. I'm not going to cross a boiling point with this since it doesn't reach 100 degrees. I will, however, cross a melting point, which is 0 degrees Celsius. So I go from -20, I go up to 0. It goes flat because I'm going through a phase change. and then I go up to 20 degrees. We got 3 segments to figure out the energy for. So this will be segment 1, 2, and 3. So let's do segment 1 first. So segment 1 is an incline, so it's going to be Q equals MC delta T. I'm looking for Q. I did forget to put the mass in the problem, so we're dealing with a 10-gram ice cube. I went back and added it right here, so it's a 10-gram ice cube. So our mass here is going to be 10. Our specific heat, since it's ice, is going to be 2.11, not the 4.18. So 2.11. And the temperature change at this segment is 0 minus -20, which is 20 degrees. So we got a 20 degree temperature change. Now let's do a little bit of algebra. So x equals 10 times 2.11 times 20. That's going to be 422 joules. And there's our first segment, 422 joules. We can do our second segment now. Second segment is a flat plane. So that's going to be Q equals ml. So Q is my x. My mass is still 10. Latent heat of fusion, since this is a solid going to a liquid, is going to be 334 joules per gram, since it's water, or H2O. So now I got 10 times 334. So it's going to be 3,340 joules for our next segment. Now we can do our last segment. The last segment is an inclined plane. So it's going to be temperature change, so specific heat. So Q is X, mass is still 10. I'm dealing with water now, so specific heat is 4.184. And the temperature change goes from 0 to 20. So that's 20 minus 0 is 20 degree change. So 10 times 4.184 times 20. I get 837. I did round that to the nearest whole number. 837 joules. Find the total energy. You're a cutie. Add Q1 plus Q2 plus Q3. So 422 plus 3,340 plus 837. And our Q total is 4,599 joules. And there's our answer. So it took almost 4,600 joules to melt that piece of ice and raise it to a temperature of 20 degrees Celsius. Let's do one more. So we got molten copper at 1200 degrees Celsius is cooled down to solidify. The copper eventually reaches room temperature at 20 degrees Celsius. How much energy was released in the process? The melting point of copper is 1085 degrees Celsius. Heat capacity is 0.39 joules per gram degrees Celsius. The heat of fusion is 207 joules per gram. So let's draw our heat diagram. So my maximum temperature is 1200. My low temperature is 20. It says the melting point is 1085. So 1085. All right, since we're cooling down and solidifying, that means our graph is going downwards. So we're going to go from 1200, we're going to cool down now to 1085. Once we hit 1085, we go through that phase change, we turn into a solid. Once the solid is complete, it starts cooling down, giving off energy again. Now, the key difference here, since it's going down, that means energy is releasing. That means our energy values will be negative. It's very important to have that negative in there to indicate that. So I'm going to label my segments 1, 2, and 3. For inclines and declines, we do specific heat. So this first decline is going to be specific heat. It's going to be Q equals MC delta T. So I forgot to put my mass in again, unfortunately, so I squeezed it in right here. We got 100 grams of molten copper. So let's continue on with our calculation. So I'm looking for Q, so Q is X. I got 100 grams. The specific key to copper is going to be 0.39. And my temperature change goes from 1200 to 1085. So 1085 minus 1200 is negative 115. That negative is very important. So make sure you include your sign. So now we multiply that out to get our energy. So negative 115 times 100 times 0.39 gives me negative 4,485 joules. Let's do our second segment. Second segment is a flat line, or it's a plane. So it's going to be latent heat, QML. We're looking for Q. My mass is still 100. And the latent heat of fusion of copper is 207. In this case, I need it to be negative because it's going to be losing 207 joules per gram. So it's negative 207. So X will equal 20,700, and that will be a negative value. It's going to be 20,700 joules. So our last segment is a decline, so that's going to be specific heat. So Q is going to be X again. My mass is still 100. My specific heat for copper, it didn't mention whether or not liquid and solid copper have a different specific heat, so we're going to assume that is the same at 0.39. Our temperature change goes from 1085 to 20, so it's 20 minus 1085, and we get negative 1065. To solve for this last X, we just multiply. So negative 1065 times 100 times 0.39, and I get negative 41,535. And that's going to be joules. And the last thing we do is find that Q total. So Q1 plus Q2 plus Q3. So negative 4,485 plus negative 20,700 plus negative 41,535. So our total energy release is going to be negative 66,720 joules. Though I guess you could also write it as negative 66.7 kilojoules. And there's our answer. And again, you have to have that negative in there to indicate you're releasing energy. Otherwise, it's inaccurate. So phase change is just taking specific heat, adding latent heat to it. You have temperature changes and phase changes. You use a graph to organize your information, and at the end, you add all your energy values to get a total energy value. Make sure you watch whether or not the temperature is increasing or decreasing. Make sure you pay attention to your state of matter, whether it's fusion or vaporization. You don't want to get those two mixed up. And use the temperature change that is specific to a segment. Don't use the entire temperature change of the problem. I hope this video helps. And as always, good luck on your tests.